In this video, we will learn about a new state variable, entropy. Entropy is going to offer us an additional balance equation to solve our problems that are related to the thermodynamics. On this corner, I have listed different statements of the second law. One will be the Clausius statement of the second law. The other will be the Kelvin-Planck statement of the second law. And also we will relate the entropy of the universe to the second law of thermodynamics. We will proceed to these laws gradually. Let's remember what we have done in the first law domain when we were calculating the work done by a gas on the environment if we lifted the weight all at once, if we lifted the weight in 2 installments, and if we lifted the weight with infinitesimal installments. Now, when we lifted the weight in infinitesimal installments, we were able to maintain the isothermal condition that our system and surroundings were in a rapid exchange of heat because the required heat was so small, the exchange was complete in sufficiently short time. But when we lifted up the weight in one single installment, the system had to lose some of its energy because the isothermal condition has been lost. And whys and hows are going to be more clear when we start learning about entropy. Now, entropy is a state variable. We will use the symbol S for the extensive, S hat for per kilogram, and S underbar for per mole entropy, intensive entropy. So this is the extensive entropy, and these are the intensive entropies. Now, what is entropy? Entropy, by definition, is heat exchanged through a diathermal wall which is trying to keep the system at a constant temperature T. Entropy is the heat exchanged with the environment through a diathermal wall. The diathermal wall is maintaining the boundary at a constant temperature T. Here, we need to keep the system at a constant temperature T. In order to keep the system at this constant temperature, we need to exchange heat with the environment, and entropy is that heat exchanged with the environment divided by that temperature. So, given these definitions, now let's start asking the question of reversibility. What is reversible? Let's go back again to the earlier example. Let's take our system where we have a slow process generating work while exchanging heat with the environment, keeping the temperature constant. In that slow process, we obtained work. The work is stored, for example, in a compressed spring, that we have a certain level of compression in the spring. And that work can be used to bring the system back to its original configuration. If we release the spring is going to compress the gas, and that compression is going to be translated all the way to the original process. So if I continue plotting this hypothetical process. Here is my isotherm. I started at P1, V1. I expanded my gas to P2, V2. So this is state 1. This is state 2. Between state 1 and 2, I had a slow process, slow and gradual process. I was able to maintain the isothermal conditions, and I had a piston and cylinder assembly, which is connected to a spring. So as the gas expands, the spring compresses, and I store this work in that spring here. Now, by some means, if I can release that spring, again, slowly and gradually, because I was able to store all the work, and the work was minus integral P dV, all right, that I could extract all of this work because I was doing this process gradually. And when I release this spring, of course, all these processes are hypothetical, but when I release the spring, it can induce all the work, and I reversibly collected my situation, reverted my situation back to the original position, and my process is reversible. Reversibility means, in other words, that nothing is wasted. However, look at this situation that I'm doing some rapid expansion. When I'm doing this expansion rapidly, I'm losing some of the work. That part is lost. That part is lost. Now I have less work available to me in that spring. As a result, I won't be able to revert back to state 1, but I will end up at somewhere intermediate if I intend to use this work to compress that gas back to the original initial state. What did I do in that rapid process? In that rapid process, I lost some of the energy irreversibly. Where did the energy go? Energy dissipated to the universe, that I cannot recover it back. How can I account for this energy that is dissipated to the universe? Using a state variable, this is my state variable. Entropy is my state variable that allows me to estimate the energy that is lost, that is dissipated to the universe due to the irreversible processes. Now I'm going to perform an experiment, and I would like you to join me doing this experiment right now or later. I'm going to rub my hands, and as I rub my hands, I feel that my hands are getting warmer. What do? I convert work of movement of my hands to heat, that my hands are warmer. Now I'm going to release that heat to the environment. The heat is being absorbed by the air molecules colliding my hands, and those molecules get instantaneously warmer, and as they move away, they dissipate the heat from my hands to the environment. All right? The same molecules, when they are bouncing off my body, is absorbing heat from my body as well. That's how I transfer heat to the environment. And as a result, I lose this energy irreversibly. I cannot collect those molecules back and ask them to transfer the energy back to my hand. The process of transferring heat from my hand or from my body to the environment is going through a natural process that heat is being transferred from high temperatures to low temperatures. That is one nature of law. So heat has a tendency to be transferred from high temperatures to low temperatures. That is the natural direction. And of course, by transferring that heat from high temperature source to a low temperature sink, a system tries to reach equilibrium with its environment. Whether it is possible or not depends on the system. Okay, so now, a couple of things to remember from this discussion. The natural direction of heat is from a high temperature to low temperature. And this is the natural direction of heat. Heat flows from a high temperature object to a low temperature object, or from a high temperature environment to a low temperature environment. Now let's take this one and let's see what Clausius has said about this process. Clausius said that it is not possible to construct a device that operates in cycle, and what it does is only to transfer heat from cold to hot. In other words, Clausius' statement says that it is not possible to transfer heat from a low temperature to a high temperature without doing anything else. So let's write this one, write this as a statement, Clausius statement. Let's amend this here. It is not possible to have a device that operates in cycle. So that's going to be my symbol, a device that operates in cycle. So this is going to be my symbol of a device operating in cycle. So we've constructed a device that operates in cycle and transfer heat from cold to hot. It is not possible to construct a device that transfers heat from a cold object to a hot object. Cyclic process is the buzzword. Device is the second buzzword. Okay? All right. On the other hand, Kelvin-Planck statement of the second law is slightly different. Kelvin-Planck statement of the second law is about how we convert heat to work. Now, I did rub my hands together. I generated heat, and that heat has dissipated to the environment. I was able to convert work to heat. And here, when I'm doing an isothermal expansion, I'm converting heat to work. Now, Kelvin-Planck statement is another device, is about another device. Again, it is not possible. Again, not possible. You have to keep that these are not possible statements to construct a device that operates in cycle. All right. And it converts all the heat to work. All right, that's not possible. Before I can go and write the balance equations to prove each and every one of those statements, I have to also give you the most general description of the second law. The most general description of the second law is that entropy of the universe always increases. Entropy of the universe always increases. And of course, when I rub my hands, when I let them cool, when the air molecules bounced off of my hands and has taken the heat away from my hands to the environment, that process generated entropy. So entropy generation is possible. Entropy can be generated. And this is another quantitative statement of the second law. Entropy generation has to be either greater than or equal to 0. Now, when a process is reversible, all right, when a process is reversible, our quantitative statement of the reversibility will be entropy generation to be equal to 0. There is no entropy generated. All right, so entropy generation also gives us clues whether a process is reversible or not. Now let's go back and let's examine the Clausius statement, the Kelvin-Planck statement, through the first law and second law analysis. Now let me divide this board so that our definitions are not going to be lost. Now we are going to write the entropy balance. The entropy balance follows the same lines as the energy balance, as the mass balance, with the additional term of entropy generation. Time, rate of change of total entropy within the system boundaries is equal to net entropy entering through the system boundaries by mass exchange, net entropy leaving through the system boundaries through the mass exchange, entropy due to heat transfer across a diathermal wall, and entropy generation. Let me also write the energy balance that accompany this entropy balance for our further problem solutions. The energy balance, if you remember, was a du over dt to be equal to the energy that comes across through the system boundaries by mass exchange, energy leaves through the system boundaries by mass exchange, energy transferred to or from the system as heat, energy transferred to or from the system as shaft work, and the PV work. All right, this is our energy balance that accompany our entropy balance. Energy balance is a conservation law. Entropy balance is not a conservation law because we have a generation term. Due to the second law of thermodynamics, entropy of the universe always increases. For the reversible processes, entropy generation could be equal to 0. But for any other process, we have to have a positive entropy generation. Now let's use these equations to understand what Clausius' statement is trying to tell us and what Kelvin-Planck's statement is trying to tell us. So let me just generate a symmetric domain. Let's leave this place blank. Let me start by the Clausius device. Now, Clausius' device was saying that it is not possible to construct a device that operates in cycle and transfers heat from a cold source to a hot sink. So let's start from a cold source. We have a cold source. We have a hot sink. We have a device that operates in cycle. And our device is transferring heat from here to here and is operating in cycle. Operation in cycle means that it starts at state 1 and it ends up at state 1. Starting and finishing states are identical. I'm going to, of course, we are now familiar with the first law. I'm going to start from the first law. Let's see which components we retain, which components drop out of the first law for our system. Now, this is a black box system. We have a black box, interior of which is not clear to us, but this black box is apparently rigid. It has only heat exchange through it, no mass exchange, no shaft work, and no surface boundary movement. No work shaft, no surface boundary movement, no mass exchange. The only exchange with its environment is the heat exchange. So let's use these concepts to complete the first law analysis. We have Q cold entering, Q hot leaving. Nothing else is happening. So I'm going to multiply both sides by dt and I'm going to integrate. The next step of analysis is the integration of the internal energy from state 1 to state 1, and that is equal to integral Q sub C minus Q sub H times dt over however long it takes for this process. So I have U1 minus U1 is equal to 0. Internal energy is a state function. That is equal to Q dot C minus Q dot H. Now I labeled not that, of course. Of course it's not that. The integral Q dot is equal to Q. Total heat transferred through this process, total heat transferred through this process. Now let's check our sign convention. I wrote incoming heat as positive, outgoing heat as negative. But I didn't have to do that. Let's just maintain the fact that we're not going to just differentiate incoming and outgoing. We will keep those heats as additive, as if everything is entering through our system boundary. But then our balance tells us that Q cold is equal to minus Q hot. So the magnitude of the heat that is being transferred to the system is equal, but its sign, their signs are different. It means that their directions are opposing. We don't learn much from this analysis until we use the second law to guide us. The second law analysis similarly goes as follows. ds over dt, time rate of change of total entropy within the system boundary, the black box, no mass exchange. We have heat exchange term Q hot over T hot with a dot. And now we are using the plus convention, Q cold over T cold plus S generated. Entropy is a state variable. Entropy is a state variable. Let's integrate. ds between states 1 and 1 is equal to Q hot over T hot plus Q cold over T cold plus S generated integral dt for the total period. This is equal to S1 minus S1, and that is equal to 0. Let's focus our attention to the other side. Now I finished the algebra here for you. The rearranged equation takes the following form, that after the integration, I take these two terms to the other side of the equation with a minus sign in front. I substitute minus Q hot for Q cold here. I take everything into the Q hot parentheses with this minus sign retained. That we have a negative term here, minus Q sub H, all right? Its magnitude is positive, minus sign makes it negative. 1 over T hot is less than 1 over T cold, and hence this group is less than 0. This group is less than 0. Heat is leaving the system boundary. It is negative. A third negative indicates that our entropy generation is less than 0. And that is in strict violation with the second law. So this device is not possible. Entropy generation is less than 0. This device is not possible. Now let's look at the Kelvin-Planck device. We will perform a similar analysis for the Kelvin-Planck device. Now the Kelvin Planck device is absorbing heat from a source, T sub h, operating in cycle, and generating work as a result. Let us have our arrow a little bit more clear. Yes. Again, we are going to do a first law analysis and a second law analysis. This device is operating in cycles, so let's have this as our point 1. It's going to be operating between point 1 and 1. It will come back at the end of the cycle to the same state. And we will show, we will look for the condition whether the entropy generation is greater than or equal to 0 or not. Now let's start from the first law analysis. du over dt is equal to, these terms are not there, so this isn't. But we have a heat term and a work term, so our first law analysis goes like this. I don't indicate that as a shaft work, I indicate that as a work in general, all right? As work in general. Now when I integrate, similarly, I get u1 minus u1 between state 1 and 1 as 0, that is equal to q plus work, or q is equal to minus work. Heat enters through the system boundary. The dots are eliminated because we finished integrating, taking the time integral. Q is equal to shaft work. We don't know whether it is shaft work or any other kind of work, with a sign difference. This is the first law. Now let's perform the second law analysis. ds over dt is equal to no mass flow rate, no mass exchange, q dot over t plus s generated. All right? Again, I integrate between state 1 and 1 to get s1 minus s1 to be equal to q over t plus s generated. This is going to be 0, or s generated will be equal to minus q over t. Now let's see. Q is coming through the system boundary, so it is positive. Temperature is absolute temperature, it is positive. The ratio is positive. The negative sign makes entropy generation less than 0, and therefore this device is not possible. So is this device. Those devices are not possible. We could only say through the second law of analysis, the second law of thermodynamics allowed us, through a new state variable we called entropy, analyzing a system and declaring whether it is possible or not. We're going to use this this property of the second law of the entropy balance to check the direction of the processes, to check the declarations of certain inventions, whether it is going to violate the natural laws, as well as to test whether a device is reversible or not. So if we summarize, we have a new state variable, which is entropy. By definition, it is Q over T. It is a state variable. It has extensive and intensive components. We can write balance equations on entropy. And unlike energy or mass, entropy is generated. And this entropy generation is how we use this balance equation to test against the nature's laws, to test the processes against the nature's laws.